Okay, so we can solve these kinds of problems analytically or numerically using essentially exactly the techniques that we've talked about in the last few lectures. The ODEs and the numerical equations get a little bit more complicated, but not much, and the steps are exactly the same. So let's do this one analytically. The steps are the same to generate the ordinary differential equation. The first thing I have to do is define a differential control volume. I have to keep in mind the extended surface approximation when I'm doing that. So my differential control volume is differentially small in x because the temperature is varying in x as I move along this fin. Right? So this is the same fin, I've just sort of rotated it 90 degrees. This is x, this is y. Differentially small in x. But it extends across the entire fin cross section in the y and I guess the z direction because there's no temperature gradients in those directions, right? That's what the extended surface approximation does for us. So there's my differential control volume. The next step is do an energy balance on that control volume. So let's see, I have energy being transferred in the x direction and energy being transferred by convection from the surface. So there's going to be an energy transfer in the x direction, q dot x, at location x, so the left side of this control volume. Same thing, but at the location x plus dx, so the right side of this control volume. And then there's convection from the control volume to the surroundings. So in equals out plus stored. There's no stored because we're still at steady state. So I have in, which is this guy, equals out, which is this guy and this guy. Here's my energy balance. The next thing I do, so step 3 is you expand the x plus dx term. So q dot in the x direction at location x plus dx is equal to q dot in the x direction at location x plus dq dot x dx times dx, right? This is what I can write if I'm going to take dx to a differentially small condition. So I take this and substitute it into here. I get this equation. I can cancel out q dot x at location x. And here's my differential equation written in terms of energy. And again, it's probably a good idea to step back and think about it. What is this equation saying? It's saying that the rate of conduction in the x direction is changing, right? dq dot x dx is not equal to 0. It's changing. So the conduction heat transfer rate is changing as I move in the x direction. That makes sense to me, right? I mean, it should change because I'm losing energy off the edge of the fin. And in fact, the reason that it changes here is due to convection, right? It's in this case being reduced. It starts out really high and it drops. And the reason it's being reduced is because I'm losing energy due to convection. So there's my ODE. I think it makes sense. I'd like to write an ODE in terms of temperature. So I need my rate equations. Let's see, I have a conduction heat transfer rate here on the left side. So I will use Fourier's law for that. Minus k times AC times dt dx. Just being clear here, this AC is the cross-sectional area of the fin. It's the area that I would see if I looked down the axis of the fin in the x direction, right? It's the area available for conduction. So I'd plop that into here. Q dot convection, I have to be a little careful about this. It's not the entire fin's convection heat transfer rate. Is convection from this little differential control volume. So that's going to be the surface area enclosed in my control volume, which is the perimeter times dx, multiplied by h bar times t minus t infinity, right? That's being faithful to the direction that I drew this arrow, right? So the perimeter here, just to be real clear, is the perimeter that's exposed to the fluid. Again, if I'm looking in the x direction, it's the perimeter exposed to the fluid. And I plug this into here, I plug this into here, and I get this differential equation for temperature. I do the usual thing here where I'm going to divide through by everything that's constant in the highest order derivative. So in this case, k is constant, AC is constant, and dx is constant. So I divide through by that, and I get this differential equation here. Right? So the steps to get this are the same. The differential equation is a little different, right? Every time we've gotten a differential equation up until now, it's been possible for us to separate it and integrate it. So they've been pretty easy differential equations to solve. it's really tempting to try to separate and integrate this one too, since at this point that's what we're used to doing. But if you do that, you're going to run into trouble. So here, I just took this differential equation and did what we've done before, which is I took the dx over to the other side here and tried to integrate both sides. So if I integrate the left side, I would have no troubles with that. That would be just the integration of an exact derivative, so I'd get dt dx. But when I try to integrate the right side, I run into issues. And the issue is that I can't integrate t of x with respect to x because I don't know what t of x is, right? So this is not a separable equation, and I can't take this approach anymore, right? I have to take a different approach to solve this equation. So we have to remember our differential equations. So this is, if I rearrange it and put it into sort of the standard form, which has all the temperature stuff on the left side and everything else on the right side. This is a second order differential equation, right? It's got a second order derivative here. It's linear. There's no products of t and dt dt, but it's not homogeneous. And what that means in this context is that if you get a solution t and you multiply that solution by any constant, the multiplied solution is not itself a solution, right? So more practically, it means that the right side here is not equal to 0, right? So second order linear non-homogeneous differential equation. So we're going to go through solving this kind of differential equation using what's sometimes called the method of undetermined coefficients. I will point out that one of the reasons why I showed you how to use Maple is because Maple is super useful for at least checking your work as you go through this process, right? I mean, I wouldn't sort of rely on Maple completely as a crutch because there's a chance in your life, like for example on an exam, you might be asked to solve one of these. But certainly it's really handy in real life as you go through the process of solving these. So the idea here then is that we're going to take our solution t and split it into t sub h, which is a homogeneous solution. So t sub h has to be the solution to a homogeneous differential equation, and t sub p, which is the particular solution, that's the solution to whatever equation we end up with after we subtract out the homogeneous solution. So this is just algebra, right? I'm just going to take this idea and substitute it in here every place I see a t. So that's what I did here and here. And here I get some stuff related to th and some stuff related to tp. And I have to remember the idea here is that th is the solution to a homogeneous differential equation. So if this is the stuff related to th, that has to equal 0, right, in order for me to have a homogeneous differential equation for h. So I'm going to set this equal to 0, and then this is whatever is left, right? And that must be the particular differential equation, right? So I just need something that solves this, and then this will be my homogeneous differential equation. So we have, at first glance, made our life twice as hard, because instead of just having to solve one differential equation, now I got to solve two differential equations. But actually, it's easier than that, because there are a whole bunch of functions that have been figured out for you that solve homogeneous differential equations, right? So this part of the problem is really kind of a pattern matching thing, right? You're going to use solutions that already exist. Now, you've used these in your life before: sine, cosine, exponentials, cosh, and sinh. We'll actually introduce you to some other ones, Bessel functions, that are just different solutions that are a little more powerful. And then this we'll use the method of undetermined coefficients for. So let's go through the process. We'll start with this here. We'll start with the homogeneous differential equation. This is a table which just gives you a bunch of linear homogeneous ordinary differential equations, and then their solutions, right, to within two undetermined constants. And again, this table is super handy. Some of this stuff down here at the bottom probably is unfamiliar to you, and we'll come back to that next time and talk about how you figure out Bessel functions. The stuff up here at the top, I'm sure you've seen before, right? So I have d squared t dx squared minus m squared times t. So this m squared, the reason they use m squared here is to make it clear that this is a positive constant. So you have the second term here is negative. If I have the second term negative, then I can choose, actually. I can either have exponentials or cosh and sinh, right? It's up to you. Just to be clear, these are different constants depending on what you choose here. If the second term is positive, then I have cosine and sine, right? So what do I have here? I have this ODE, this coefficient here multiplying the second term is perimeter, h bar k, ac. None of the things in this group can be negative. So this has to be a positive constant. So this is d squared th dx squared minus m squared th, right? Where m squared for this case is perimeter h bar over KAC. So I have this case here, and I can choose which of these two solutions I want to work with. Whichever choice I make, I'll get the right answer, right? So there's no problem with that. Sometimes it's easier if you choose one thing than the other. What I have found is that if you have a computational domain that goes to infinity, it's usually easier to choose the exponentials, because usually then as you go to infinity, one of these exponentials at the boundary will disappear. If you don't, then it's usually easier to use cosh and sinh, and that's what we have here. We have a computational domain that goes from 0 at the base of the fin to L at the tip of the fin. So I'm going to use cosh and sinh, thinking that probably this is going to be easier to work with. So here's the solution to my homogeneous differential equation. Again, I didn't really solve this. I sort of just stood on the back of mathematicians who already have solved this for me, and like a monkey, I pattern matched and figured out what it is. And again, Maple is super helpful for this. So there's my homogeneous differential equation. C1 and C2 are undetermined constants, so we'll come back to those. Here is my particular differential equation, right? So if I go back here, this is this part of the equation right here. And this is what I have to solve using the method of undetermined coefficients. And the method of undetermined coefficients is actually pretty easy once you get the hang of it, right? The idea is that you essentially look at the right side. So you look at the non-homogeneous part of the equation, the right side of the equation, right? If it were 0, I'd have a homogeneous differential equation. It's not, so I don't. And you identify what functions live over here, right? And by what functions, I mean, is it a constant? Is it something with x squared in it, or an exponential or a sine, or what is it that sits over here? And then whatever it is, you put that into your particular solution multiplied by some undetermined constant. And the other thing you have to put in your particular solution is the derivatives of whatever you find over here, right? So you put C3, which is an undetermined constant, times the function on the right-hand side, plus C4 times the derivative of this function. If there's more than one function here, you would keep going, right? In this case, it's really easy. If I look at the right-hand side, what function do I have here? Well, this is just a constant, right? So I can just take C3 times a constant, which is 1, right? And then C4 times the derivative of the constant, which is 0, right? So in this case, I just get that TP, it must be some constant. And I take that basically hypothesis or functional form for TP, and I just plug it up here into this equation, and I make it work. I adjust the undetermined constants until it works. That's what makes this the method of undetermined coefficients. So if I plug in TP equals C3 up here, what do I get? If I take two derivatives of a constant, I get 0. So that's 0 minus the perimeter times h bar over KAC times the constant, and then whatever I had on the right side. And if I just divide through by minus perimeter h bar over KAC, I find out that in this case C3 must be T infinity. So TP in this case is T infinity. And we can come up with practice problems, or maybe your homework will have something a little more interesting where the right hand side is not just a constant, but the idea remains the same. Whatever it is, if this were a sine, then you would have some undetermined constant times the sine function plus some other undetermined constant times the derivative of the sine function, which is a cosine function, right? And you would just take this idea, plug it into here, and adjust C3 and C4 until everything worked, right? So that's the method of undetermined coefficients. At this point, I have my solution then, right? I have the homogeneous solution. I have the particular solution. So this is my solution, right? It's I got Cosh and Cinch, and then my particular solution is T infinity. So this is my solution to within two undetermined constants, right? This is my general solution in that no matter what I pick for C1 and C2, I'm going to satisfy this differential equation, right? So the way that I pick C1 and C2 is I have to also satisfy my boundary conditions, right? So your boundary conditions are at the boundaries of your computational domain. So for us, the boundaries of the computational domain are x equals 0 and x equal L, right? At x equals 0 here, I have a set temperature. So T at x equals 0 is the base temperature. At x equal L, I don't know what the temperature is, which right away tells me I have to do an interface energy balance, right? I have to make sure energy works at that boundary. So here at this boundary, I will do the usual thing where I'll put one control surface just inside the boundary. So at x equal L minus, I'll put the other just outside the boundary. We're going to assume that the tip of this fin is adiabatic, so it's not convecting, it's just insulated. And what that means then is that whatever comes in to the left side of this boundary, so this is the conduction rate of heat transfer at x equal L, has to equal 0 because nothing's leaving to the right side of the boundary. You'll notice I don't have any convection coming out the sides of this because this is infinitesimally small, right? There's no surface area exposed to it, just like there's no heat capacity in a transient problem, right? All right, so if I plug in Fourier's law into this equation right here, I get minus Ka dt dx at x equal L has to be equal to 0. And in this case, K and A are constants, so I can divide through. So I get that the temperature gradient here has to be equal to 0. So these are my two boundary conditions right here. I have to get C1 and C2 selected so that this happens at x equals 0 and this happens at x equal L, and then I'll have the right solution.